Right, so at the end of the last section we had a look at how many signals we would expect to appear, and I would like to encourage you to always try and look for symmetry in molecules to try and predict where signals will double up or where they will be separate from each other. But NMR has other aspects that we can look for that give clues as to the analyte of interest. And the second thing we need to look at beyond simply chemical shift is the integration of signals. So please always look at the bottom of the spectrum for these numbers. You'll see they're written in red here. These numbers here are the areas of the signals, and those areas are really important. They tell us how many protons, how many hydrogen nuclei are giving rise to each particular signal. So you see the 1.52 here, the 1 and the 2.53 are showing a ratio over here. Have a look at the molecule of interest, and the molecule of interest over here you'll notice has 3 protons giving rise, 3 chemically equivalent protons giving rise to a signal, 2 chemically equivalent protons giving rise to a signal, and a whole mess of protons that give rise to an overlapping set of signals. So there are 5, 2 and 3, and you can notice then that if you multiply these numbers by 2, you end up getting a ratio of 3, 1.5 times 2 is 3, is to 2 is to 5, meaning that C is that group over here. Those 3 protons are giving rise to this signal. Those 2 protons are giving rise to the signal that is 2, and these are giving rise to the mess that is at 5. So please multiply. If you multiply, make sure that the areas, the integration matches the number of protons in your compound, and if you have to multiply to do that, that is fine. So have a look here. I have got a total of 12 protons in this compound, but you'll notice the integration here is 1 and 3 is a total of 4. Can you see that in order to get the spectrum to match the compound of which it was taken, we're going to have to multiply all of these by 3. So if you multiply it by 3, you'll get 9 and 3, which makes it a total of 12. Then have a look at the chemically equivalent protons that we have available. If you have a look at the chemically equivalent, you'll see that these 3 are equivalent to each other, and so they must be giving rise to this signal, and these 9 are equivalent to each other, so they must be giving rise to the larger signal. So the integration of signals is really important. It tells you how many of a particular nuclei are giving rise to that particular signal. Just please be aware that this integration only works for proton NMR. It doesn't generally work for other types of NMR, and certainly not for carbon-13 NMR in the normal form that it is run. Okay, so we are able, simply by looking at the areas that are available to the integration of the peaks, we are able to determine and assign signals to tert-butyl acetate. Okay, so just please, where we're at this point, don't forget chemical shifts, the shield and deshielding, determine where signals for chemically equivalent nuclei appear. Don't forget that, and you can use tables to identify the chemical functionality in a compound. And we have another tool available to us, is the integration of the signals, which gives the relative number of protons in a proton spectrum. Okay, but there is a third area of information that comes from NMR, and I think this is the power of NMR, comes from this third area. Have a look here, look very carefully here. This is a spectrum of ethyl acetate, a proton spectrum of ethyl acetate, and simply by looking at chemical shifts, we can see that this signal over here must be the CH2 that's next to an oxygen, but we have two CH3s, and it would be interesting to see if we can distinguish between them. If you look very carefully at the spectrum, and I've zoomed in, you will see that the CH2 that we had identified appears as a quartet. It's split into 4 peaks. Its signal is split into 4. And one of the methyl groups, actually it is a methyl that's right next to the CH2, is split into 3 peaks. It appears as a triplet. We can see from the integration that it is 3 protons, and we can see that this is 2 protons for the CH2. But it's interesting to note that this methyl group here is a triplet, and the CH2 right next to it is a quartet. Those two are interacting with each other in some way, giving rise to the signals that you see. Don't forget this methyl group at the end here, which has no protons around it. It's isolated in terms of neighbors, which appears as a singlet on the NMR spectrum. So it'd be interesting to explore. So we know where the CH3CH2 is. You could use chemical shifts to identify a methyl next to a carbonyl at being around about 2, and the other methyl group is over there. Okay. The CH3CO, this one over here, has no neighboring hydrogens, so it has no splitting. The reason that this one appears as a triplet is because of its neighbors. If you have 2 neighbors, see this methyl group's got 2 hydrogens near it. If you've got 2 neighboring protons near you, then you're going to split into 2 plus 1 is 3. And this CH2 here has got 3 neighbors, and so it's going to split into 3 plus 1 is equal to 4. So splitting is due to neighbors, but maybe I can just explain why this is. But the rule is, if you've got 1 neighbor, you're going to split into 2. If you've got 2 neighbors, you'll split into 3. If you've got 3 neighbors, you'll split into 4. And of course, if you've got no neighbors, you're not going to split at all. So it's always the n plus 1 rule, looking at your neighbors. And this methyl group has got 2 neighboring protons. This CH2 group has got 3 neighboring protons. And this CH3 group has got no neighboring protons. So let's see why this is. So the question might be, why would this methyl group appear as a triplet? Well, remember that its neighbors are in a magnetic field, and those neighbors, those neighboring nuclei, would have to be aligned with or against the magnetic field. Now, there are many ways for it to work. You could have this neighbor with the magnetic field and this neighbor against the magnetic field, or this neighbor with and this other neighbor with. So there are several situations. You could have both with the magnetic field, you could have one against and one with, or one with and one against, or you could have both against the magnetic field. When both of them are aligned with the magnetic field, they cause the methyl group to see a greater magnetic field, and so you will see a signal at a higher magnetic field. Of course, it doesn't matter if this is against and that's with, or that's with and against, but of course a quarter of your sample will have this situation, another quarter of your sample will have this situation, and those two will work together. Those two have the same effect on the methyl group, and so you will see that this methyl group is not affected then when they are opposite. But of course, when they're both against the magnetic field, then of course your methyl group is going to see a much lower magnetic field and a lower frequency. This gives rise to this methyl group having this appearance over here, with a higher frequency due to neighboring both with, and a lower frequency both against, and a large proportion unchanged, due to the quarter of a sample, half a sample, that does not change the frequency or the magnetic field of that methyl group. That's why having two neighbors splits you into three. Again, so why it's a triplet, in its neighbor, each nucleus has to be with or against the magnetic field. There are four possibilities that influence it in three ways. But of course, the central probability is much greater because there are two sets that lead to no change in the signal. So we've got another question, is why would this CH2 here appear as a quartet? Well, it's got three neighbors, and now we've got 8 possibilities for those three neighbors. All three could be with, or you could have two with the magnetic field, one against, or two against, one with, or all against, and all of these possibilities affect the CH2 in slightly different ways. And you'll find that a very small 1/8 of your sample gets affected, such as it has a high frequency. 3/8 have a slightly higher frequency, 3/8 have a slightly lower frequency, and 1/8 has a very low frequency due to the presence of that methyl group next to it. So the splitting is due to the neighbor. Don't forget that. And if we can reinforce that, why is it a quartet? In its neighbor, each one nucleus, 1H nucleus, each proton has to be with or against the magnetic field. There are 8 possibilities that influence in 4 different ways. Okay, the question, why is this a singlet? Well, there are no neighbors right next to it, and so there's nothing there to influence the methyl group, and so it will be a singlet. So signal splitting can be more complex than that. So you can see we normally use the n+1 rule for that, and this n+1 rule works for spin half nuclei. If you've got n equivalent neighbors, you split into n+1 peaks in the NMR spectrum. So you can see this methyl group has no neighbors, so it'll be a singlet. This hydrogen has how many neighbors? It's got 1, so it's going to appear as a doublet. 1 + 1 is 2. See this CH2 group here? How many neighbors? It's got 2 neighbors, so it'll appear as a triplet. This one has 3 neighbors, so it'll appear as a quartet. This is an interesting case. This proton has got 6 equivalent neighbors, and because it has 6 equivalent neighbors, it will appear as a septet. So splitting and spin splitting is really important because it shows how each signal is split due to the neighbors. Now, be careful in this case because protons that do not spin split are ones that are equivalent. So you see over here, notice that each of these are identical. This molecule is perfectly symmetrical, so the methylenes are perfectly identical to each other, and so they cannot split each other. In benzene, if you run proton NMR of benzene, you get a single signal with no splitting. All of these are identical to each other, so they can't split each other. Also, please note that protons further than 2 carbon atoms apart do not normally split. So you won't see a doublet here. These will both be singlets for the purpose of this course because they don't have neighbors. But this one will appear as a doublet because it's got 1 neighbor, and this will appear as a doublet because it's got 1 neighbor, if these are different to each other. If they're identical, of course we won't see that at all. Okay, so please note that all of these will be a single singlet. We'll have, in benzene, you only have 1 signal in the proton spectrum. And please note as well, a point is that OH also does not normally cause splitting. So if one of these was an oxygen, if there's an oxygen here, there's fast exchange of the hydrogen away, so that hydrogen's never home, and so the hydrogen's not going to cause splitting with a neighbor. It's not going to act like a true neighbor, and so it will not cause splitting. Okay. Please note that, of course, that in a compound such as this one, if you've got this signal appearing as a quartet because it's next to the CH3, and this one appearing as a triplet because it's next to the CH2, the difference in frequency between the different peaks in the signal are the same. And so this distance here of 7.2 Hertz will match for both signals. It's called a coupling constant. The groups of protons coupled to each other must have the same coupling constant. So this quartet here, for those which have 3 neighbors, this quartet will have the same coupling constant as the triplet, because it's got 2 neighbors, because those are interacting with each other. And so that's another thing to look out for that. So please, at this point, note that there are 3 things to look out for on an NMR spectrum. 1, look for the chemical shift. If you've got the chemical shift, then you know you can pick out chemical functionality. Second thing, look out for integration. If you've got integration, then you know how many protons are giving rise to a particular signal. And thirdly, please look out for signal splitting. Signal splitting shows the neighbors. If you've got 1 neighbor, you're a doublet. If you've got 2 neighbors, you're a triplet. If you've got no neighbors, you're a singlet. If you've got 6 neighbors, you're a septet.